Here is a design of our BJT fixed bias configuration. This circuit is called fixed bias circuit because the transistor-based current, IB, remains constant for given values of VCC, and therefore the transistor's operating point must be also remain fixed. For fixed bias circuit, the emitter junction is grounded, therefore the value of VE is equals to 0. For this BJT circuit design, we use NPN type of transistor, 15 volt of VCC, 750 kilo ohm of RB, 2.2 kilo ohm of RC, and 150.54 of beta value.
To obtain this circuit design in this MATLAB simulation, we use DC voltage supply VCC with value of 15 volt connected to base emitter loop at our left side and collector emitter loop at the right side. For base emitter loop, the voltage supply VCC is connected directly to the resistor RB with value of 750 kilo ohm, while at the collector emitter loop, the voltage supply connected directly to the RC with a value of 2.2 kilo ohm. After that, we connected the resistor RB and RC to our NPN transistor. Okay, then we connect the RB resistor to the base junction of the transistor and the resistor of RC to the collector junction of the transistor. Lastly, we connect our voltage source VCC and emitter junction to the ground.
After run this circuit, we got 18.932 microampere of IB, 2.85 milliampere of IC, 2.8689 milliampere of IE, which approximate to IC value, and 8.7301 volt of VCE. Here is a design of our clamper. It has a capacitor connected directly from input to output with resistive element in parallel with the output signal. The diode is also parallel with the output signal, which have a series DC supply as an added element. For our circuit design, we use 35 volt of Vin, 1 microfarad of capacitor, a silicon diode series with 9.6 volt water supply, and 10 mega ohm of resistor connected in parallel. We put voltage measurement at input and output terminal and connected directly to the scope to see and observe our output waveform. While running this circuit, we can see the output parameters on our right side. The blue waveform represents our input voltage, which is 35 volt. The yellow waveform represents our output voltage. For first positive cycle of voltage input, we got 10.323 volt of our voltage output. For the negative cycle of voltage input, we got negative 58.643 volt of our voltage output.
This is the comparison of all parameters that we use in our calculation and lab circuit design. For BJT fixed bias configuration, we got 768.82 kilo ohm RB and 2.14 kilo ohm RC for our calculated value. We use 150.54 for our beta, 2.8 milliampere for our ICQ, 15 volt for VCC, and 9 volt for VCEQ. From there, we got 18.6 microampere for IB, 9 volt for VC, 0.7 volt for VB, and 0 volt for VE. In our lab circuit design, we use standard value of commercial available for our resistor. We use 750 kilo ohm for RB and 2.2 kilo ohm for RC. From there, we got 8.73 volt for VCEQ, 2.85 milliampere for ICQ, 18.932 microampere for IB, 8.73 volt for VC, 0.8 volt for VB, and 0 volt for VE.
Okay, so here are all the parameters that we use in our clamper circuit design. Okay, we use 35 volt voltage input for first cycle and negative 35 volt voltage input for second cycle. From the comparison that have been made, we got 10.3 volt output voltage in the first cycle and negative 59.7 volt output voltage in the second cycle for our calculated values. Okay, while in our lab circuit design, we got 10.323 volt output voltage in the first cycle and negative 58.643 volt output voltage in the second cycle. For both theoretical and simulation clamper circuit, we use silicon diode, 10 mega ohm for resistor, 1 microfarad for capacitor, and 9.6 volt battery as our added element. Okay, that's all from our group. For group G, set 09. Thank you.